As an example of how the mole is very useful for figuring out how much stuff to use in a chemical reaction, let's imagine we're burning some butane from this bic lighter here. Now butane is C4H10, which we can show here where black is carbon, white is hydrogen. When you burn stuff, it combines with oxygen, and we've shown some oxygen molecules here, O2. And like so many combustion reactions, it makes carbon dioxide and water. Now let's try to balance this. If we start with 4 carbons, we better end with 4 carbons. So I'm going to put a 4 there. If we start with 10 hydrogens, we better end with 10 hydrogens. Well, 5 pairs should do it. And I can fix oxygen here because this looks good. It's balanced for carbon and hydrogen. I'll just total up the oxygens and put the right number there. 4 pairs makes 8. 5 singles is 8 and 5, which is 13. Yuck, but that's okay. I'll just call this 6.5 for now. And we're balanced. 1 to 6.5 to 4 to 5. Now I can't imagine a half a molecule here or half an atom. So let's just double everything to keep that ratio the same and end up with whole numbers. Now, why do they have to react in that ratio? As that animation showed, and I'm going to repeat it for you, this works out perfectly, right? 2 of these will combine with 3, 6, 9, 12, 13 of those. And did it make 8 carbon dioxides? 2, 4, 6, 8. It did. Did it make 10 water molecules? It did. So I hope you see that that's the perfect match when you react in those amounts. One other thing is it gives you an idea of how much to use. The bigger atoms are going to weigh more. You're going to need more. The little atoms, like hydrogen, weigh less. You're going to need less. The numbers on the periodic table are very helpful here. And here they are for the 4 most common elements used in chemistry for chemical reactions: hydrogen, oxygen, nitrogen, and carbon. 95% of our body is composed of those 4 elements. And rounded to the nearest whole number for simplicity are the molar masses. You may recall oxygen is 16 times as massive as hydrogen, and here's some relative numbers for the rest. We can use these. Suppose we want to do this on a molar scale. No problem. Let's just take 2 moles of this stuff. What does it weigh? Each carbon weighs 12. That's 48. Each hydrogen weighs 1 gram per mole. I think we need 58 grams for 1 mole, but it's doubled, so we're going to take 116 grams of butane. We better also have available 13 moles of oxygen. Usually we just use the air, which has excess oxygen, but if we needed to measure it out, it should be 13 times, well, each oxygen is 16, 13 times 32. Let's think, I guess that's 416 grams. That will make up to how much carbon dioxide? Well, let's add it up. 8 moles. Each mole has what mass? 12 for the carbon and 32 for the oxygen. That would be 8 times 44, which is 352 grams. That's how much CO2 this will produce. And how much water? It's handy to recall that water is 18 grams per mole. 1 for each hydrogen and 16 for the oxygen. 18 times 10 is 180. Did we do it right? Well, we started with 532 grams. We ended with 480, 532 grams. This sounds right. This is the real power of the mole. You want to actually do this stuff? Grab 116 grams of butane, make sure you have at least 416 grams of oxygen, light them up, and that's exactly what you'll make. Don't want to do that much? Do it on a tenth of a mole scale, 11.6 with 41.6. This is how the mole is used in balancing chemical equations.